Oh, hey, good to see you there. You're back for even more of the Empowerment Project. It's amazing. So today's lecture is going to include some multiple regression, a presentation on it that's a relatively brief presentation, and then some R practice. So I'm going to teach you how to do this. It's going to be an exciting and stimulating session, I hope. This is an important technique. A lot of people use this, and if you're going to, I mentioned in the last video, which you might have skipped, multiple regression is an analysis technique that's often used, and it is a good framework or foundation for all kinds of different styles of analysis and all kinds of areas in society. Actually, it's good in science, and if you're going to continue and use data analysis in your daily life, then you probably want to have at least some exposure to multiple regression, so you have some notion of what's going on. So far in class, we have focused on testing variables one at a time. So this is field goal attempts and points by LeBron James. This is one predictor and one response variable. I talked about this in a separate session, but again, you might not see it because you can skip these. These are not required. There's no points. This is entirely about empowering you. And so some of this is going to be a little bit repetitious, but not too much. So in simple linear regression is a way of understanding the relationship between variables where the data analyst assumes that one variable, the predictor or independent variable, drives a second variable, which is the response or dependent variable. I might use those terms interchangeably and not even know. So I'll just identify them there for you. This is extremely useful in most biological situations. We also can find other variables. So for example, in this case, we have age in days and wing length. This is a bird. So as the birds get older, they get longer wings. Okay, that makes sense. Sparrow wing length as a function of age. This is some other book. So what I want to say about this, though, is other things could also influence wing length. So nutritional status or some other factor. So you might want to build a more complex model. Okay, so here's another example, stem density and above ground biomass. That's just like how much biomass is in the forest. So you get more trees, there's more biomass, but there's other things probably involved as well. So nitrogen or diversity, and you might want to put all of this together into a single model. Have one model that explains the variation. And so, oh, yes, polynomial regression. By the way, what I want to say is that polynomial regression itself is not a form of multiple regression. It's different. It's just a shape. It's just putting a curved line through a cloud of points. Now, here's an interesting piece. You can have polynomial relationships within the context of a broader multiple regression, but it itself, polynomial regression is not multiple regression because you only have one predictor and one response variable. And in multiple regression, we're going to have multiple predictors and one response. So in this case, we had diversity and cover, and then cover squared. And I mentioned before, so this is just a difference between a straight line fit and something that's curved. And what I want to say is that that part of the lecture, the polynomial regression, was just to get you started down that path. You can put different shapes of curves. You can have an exponential curve, on and on. It's still a useful tool, and a quadratic curve did fit this line better. Probably better than you could find some other fit. Anyway. Okay, so a scientist, for example, could measure a bunch of different plant species growing in some plots and want to analyze the diversity or cover of those plants. So that's one response variable, cover, how much herbs are there. And we might measure a bunch of things about the environment or the soil, like soil pH. And the scientist could have this one response variable and then a matrix of many different environmental variables. This would apply in microbiology as well, of course, if you say, okay, what are all these different factors that could drive infection rate or something? So you could have multiple predictors in a single response variable. Okay. In biology, we may be collecting a slew of values that might serve as predictors for a potential response. So this is like an example of predictor variables that might be used in a multiple regression. So here are plots, and you could have other kind of samples, right? Blood samples or serum samples or samples off a swab of some kind for a microbial community or whatever. And there's a bunch of different things about that swab or the species or organism or plot or sample that you've also measured, including like a pH or phosphorus or manganese or cation exchange capacity or something. And I say, okay, all of these different environmental variables that are about the plot, or it could be some other kind of sample. Does it predict the diversity, or does it predict the presence, or does it predict the cover or something of some response variable? So you can envision this like you have a pool of predictor variables that you have to sort among and decide which go into your model. That's the task of multiple regression. Okay, so or basis cover, for example, in a forest equals, we're going to build this model, pH, soil pH, okay, some other factor, and we can pool a predictor variable from this pool, P-U-L-L, pull from this pool, P-O-O-L, into your model, and then build a model that describes our basis cover, and then you have some characteristics of that whole model that you can use to express your confidence, like R squared or p-values. That's how this all works. Now, I want to borrow from this book by Michael Crowley, Statistics, an Introduction Using R. He has a chapter on multiple regression, and I very much enjoy this opening. And you might not fully grasp it. I just let this flow over you. However, his take on this is, I think, very, very good. So in multiple regression, we have a continuous response variable and two or more continuous explanatory variables. They're not categorical explanatory variables in this, what we're talking about here, although I will tell you how to do that in just a second. Just say the words out loud. So multiple regression is the most difficult of all statistical models to do well, if that makes sense. So we also often have a great many, so they're often observational rather than controlled. We often have a great many explanatory variables. We sometimes have few data points. This is a sample size issue, and so on. There are major issues about which to include. There could be curvature in this. There might be interactions, and we can end up with a lot of parameters in our model. Parameter proliferation is what he calls it. So this is just like a framework for multiple regression and what this means. The basic idea is we're going to build a model like this, and what goes into this model, especially if we have a whole bunch of things in the pool, figuring out which ones and are some of those relationships curved and are there interactions among them is a challenging task. Okay, so we're going to build this model together. So how do we proceed with this? What's the process of finding what the best fit is, or what the best suite of predictor variables should you include in your final model? So there's different kinds of ways of doing this, and I'm just going to briefly outline a couple of those. There's something called forward selection, which is you select a variable that forms the best regression relationship with the response variable. That's the task. All the variables are in the pool, and then in a stepwise fashion, we throw back in the weaker ones. So we put everything in, and we throw back in the weaker ones. And we repeat step 2 until the variables no longer make sense or makes the relationship stronger. Okay. So we're adding in variables and throwing back weaker ones. We also could have backward selection, which is we start with all the variables in the model, and then we test this model, then we throw back one, then we run it again, then we throw back one, then we run it again, then we throw back one. So there's forward versus backward selection. Well, you don't have to worry too much about that. We're going to use one way of doing it in this class, but if you start to do multiple regression yourself, one thing you have to figure out is, am I going to do forward selection or am I going to do backward selection? Okay, so here are some important issues. The basic idea of forward versus backward is, do we start with all, there's nothing in the pool, or do we start building it this way? There's not, everything's in the pool and we just add one and add one and add one and add one. Okay. If you didn't get that, just let it go. It doesn't matter. Later you can figure it out and read about which one you want to do. It doesn't really make much difference anyway. How do we evaluate the models? What about correlated variables? And what are the categorical variables? Or what about categorical variables? These are some things that we need to chase down together here. Okay. So how do we evaluate these models? So here is an example of a model that has herbaceous cover, pH, phosphorus, CEC, Ca, slope, elevation. Here's a model that has herbaceous cover, pH, P, slope only. So these are not here. So those are back in the pool. So how do we figure out which of these is the best one to use ultimately? And just to say, this is the task. For multiple regression, the task you have is deciding which model you're going to use. Okay. Now, Crowley has some interesting things to say about this, and I think this is extremely, even better than the previous slide from Crowley. This is probably the best thing I've read in a book for a long time. If there's a temptation to become personally attached to a particular model, statisticians call this falling in love with your model. You should remember the following truths. A, all models are wrong. So we're not going to build, you will never, no one will ever build a perfect model. Okay? It's wrong. That's not the question. The question is whether it's the best one available. Some models are better than others. So all models are wrong. Some are useful. Some models are better than others. We will never know for certain which is the best. And here's the piece that's really important. The simpler the model is, the better it is. So you have to be selective. That's what I want to say. Okay, so how are we going to evaluate models? We're going to use something called the p-value, which you already know about. We're going to use the r-squared. We're also going to use this thing called a Kaki information criterion. You can look that up, AIC, in some detail if you'd like, but I'll talk to you through that when we get to the R portion. Okay. Oh, what about correlated variables? Oh, wait, so before I go there, I just want to say, how are we going to select which variables to include in the model? Part of what we want to do is this follow what's called the law of parsimony. The law of parsimony is saying you can look that up too, the simplest model is the best model. And so if we have correlated variables, we want to kick those out of the model. And we want to apply Occam's razor. Here it is. We're going to use this to carve away extraneous variables out of the model and come up with the simplest and strongest version. This comes from Occam, Willem of Occam. This is an image of him. He's a spectral character. That's Occam's razor. You need it very much. You very much need it in multiple regression. So here's how we apply it. Here is how we apply Occam's razor. P.S. Michael Crowley is calling out Occam's razor too. I borrowed this from Michael Crowley. He had it before. Now I've got it, so it's no problem. I'll give it back to him later. Okay, so it's a vital tool in choosing one model over another. And here are the things. Other things being equal, a model with n minus 1 parameters is superior to a model with n parameters. In other words, fewer parameters, better. A model with k minus 1 explanatory variables is superior to a model with k explanatory variables. So predictor variables, let's subtract them to create the simplest model. Response variables, subtract, maybe you only have one. A linear model is better to a curved model. Linear models are simpler versus a curved or a polynomial model. And a model without interactions is better than a model that contains interactions among the variables. The point of all this is subtract parameters if you can, subtract complexity in the model, no interactions, no humps is better. The simpler model is the best option. Apply Occam's razor. possible. Okay, so here's what you're going to do. So other considerations include, we want explanatory variables that are easy to measure. We want things that have a sound mechanistic understanding. We want this whole thing to be as simple as possible. We want to remove non-significant interaction terms. We want to remove non-significant quadratic or nonlinear terms. We want to remove non-significant explanatory variables. And then we want to group together factors that do not differ from one another. So we're going to remove correlated variables if possible. All of this is a exercise in simplicity and simplifying. And you're going to see, I will show you this. I will show you when we get to the R portion. The data set we're going to work with is the Lebron James data set, but I'll show you another one. I mean, you can start your whole analysis with 20 or something, 20 or something variables. And so having fewer or simplifying is the task at hand. Okay, so what do we do about correlated variables? In fact, as suggested by Crowley, we should remove any factors that we can that are containing the same information. This is called a multicollinearity. So strongly correlated variables effectively contain information and should not be inserted in the model. They both shouldn't. You have two things that are basically telling you, communicating or containing the same information. You should only have one of those in your final model. So you have to assess multicollinearity among your variables and eject one. Eject ones that you don't need. In fact, some techniques involve calculating what's called a variable inflation factors, and then we can eject things that are highly correlated. We're not going to do that in this class. The whole point of this slide is just to say, if you get involved in a multiple regression exercise yourself with your own data, you need to think about what's correlated and what's not. And if you have really strongly correlated variables, you only want one of those in. You can't have them both. And choose which one you're going to keep. There's a process for that that you have to go through. Oh, I say consider a correlation matrix. We talked about correlation before, but one thing I'm going to suggest you do right off the top when you get started with a multiple regression model is think about creating correlation matrix or other method of looking at correlation, so you can start off your approach by seeing which variables are correlated with one another. That can be a really helpful part of the process. Couple more things. One is that you can have multiple regression that includes yes, no, or categorical variables. This is called logistic regression. We're not going to do that here. You can have logistic regression with a single predictor and multiple responses. That becomes complicated. We're not going to do it in this class. You can have yes, no variables. You can have multiple levels of a variable. You can have a categorical response and multiple predictors that are continuous. You can have a continuous response and multiple predictors, some of which are continuous, some of which are categorical. Again, parsimony and Occam's razor suggest make the simplest model you can, but if you end up in a situation where you have yes, no, you can build a multiple regression model that includes it. We're not doing it in this class, but I want to say that's possible. Now, here's a flow chart of concepts. This is not like our best practices where I said concepts, not best practices, because if you're going to do multiple regression, you're going to probably need to explore packages or come up with, this is the technique you're going to follow. What I'm going to show you here in this exercise and this lecture is basically framing up the concept or what you're trying to get done. And we will go through a process in R that works, but more important than, instead of like ANOVA where we had really yes, no, and forking, I didn't want to put that here. I just wanted to just talk about the sort of steps you would go through. So you want to examine the overall correlation structure in your data set. You probably only want numbers in the matrix unless you're going to do logistic regression, and that's a different, the RO plane has to take it. You got to think about that. Just slow down. It's possible. There are no imposters. You can do that. You can do logistic regression. You can do multiple logistic regression. If you can follow the stuff we've done in this class, you can do all of that. But you're going to have to stop and think about it. So for the purpose of what we're talking about here, we're just going to deal with continuous variables, okay? And one thing I would recommend is visualizing the test of pairwise relationships. So correlation matrix, plot of all pairs. I demonstrated this earlier in the semester at one point. This panel smooth, you can see everything. Then you're going to build and test the model. We can write a full model, and I'll show you how to do that. And then we have the step procedure, which is built into the base. Excuse me. The step procedure, which is built into the base function of R. Now, some people you work with, some PIs might really want you to pick up a package and not work in base R when you do multiple regression. And if you encounter such a person, what you do is go, okay, that's fine. You just pick up whatever tool they're offering and put that in your toolbox. That's fine. Now I'll show you how to code this up in base R, and then which is what we've done all semester. And you can actually assess selected models. Once you start narrowing the variables down, you can build like I'll show you how to build like little models and then compare them using ANOVA. And we can use p-value, R-squared, and AIC. Then we're going to apply Occam's razor and finalize the model. We're going to review individual bivariate relationships, and then we're going to choose a model that balances simplicity with explanatory power. That's the Occam's razor piece of it. Okay. So now we're going to move over to R. I recommend that you establish and set up the appropriate coding music. Do that now. Switch to R and set up your coding music. We're back. Okay, so we're going to work with the Lebron James data set again, one last time. And so read the data in. Let me blow this up a little bit. We're not going to be really plotting today. So we're going to really be working in the console. Oh, there will be some plots, but you don't end up with a plot with the multiple regression. It doesn't work like that. You can't have like a box plot that you're going to present. Later, you're going to present in your paper, you're going to present regression coefficients. You're not going to present a model that has all these factors in it. So I can blow this up a little bit bigger. So we're going to take a subset, and other places in the class I have talked about subsets a lot. In this case, I'm just selecting these, and please just type these in, and let's just work with this set of this subset particularly. That'll help. So code up the subset. Okay. So now I have a subset of the data. You can go back and look and compare and contrast what we've done. Here's the original data set, which is this long data set. Has all of these values in it. We're going to take a subset of those variables to work with in this particular exercise. Figuring out which of these to take is part of the process that you might need to go through. But for the purposes, it's like if you have 20 variables or whatever, but for the purposes of what we're going to do today, let's just take this subset because I want to be able to make some progress. If you're doing multiple regression, by the way, and here's the subset, it's just this set of data. So we have this ultimately is going to be the response variable, and these are going to be all the potential predictors. If you're working with multiple regression and you've at the end of your thesis or in the middle of your dissertation or something, you got, oh, I've gone into the field, I've measured all this stuff. This is not going to be something that's done in an afternoon. Okay, you're going to spend time on this. So, but for the purposes of what we're doing right now, and you need to do exploratory data analysis. You need to explore this thing first and foremost to figure out how to proceed. But for the purposes of what we're doing today, just to get this done, let's just select this subset and just select this subset and go with me. Now, I already taught you how to do a correlation matrix. This is the code for that. This is a good way to take a look. And remember, this is there's 1, 1, 1, 1, 1, 1, 1 all the way down this way. And then this is what we're really interested in this particular situation is what are the relationships of these different variables to what we're going to call the response variable. Oh, by the way, the overall goal of what we're doing here, I'll say goal of this exercise to predict number of points LeBron scores. So that's what we're doing in this. So you may have some other thing. You may have, you know, presence of beetles on a flower or something. And just ride this. Okay, I understand it might feel a little bit silly to use the data set for this purpose. Like, can't we just watch the games? The purpose of this is simply to do a multiple regression exercise. So points is going to be the response variable, and these are all going to be predictors. Now, you already probably understand these, but the purpose of using LeBron James data all along has been you do understand what this is. You know what an offensive rebound is. Most of you do, or we can at least go see that online. It's easy to understand. Okay, so here's the correlation matrix. Now, I also taught you how to do this panel.smooth. And this is just an exercise, again, in before you begin building your multiple regression model. It's useful to take a look. This is part of exploratory data analysis. So you can take a look and see what you think is really strong. Like, oh, here's a really strong relationship. Some of these relationships look a little curved, so that's interesting. If you just go across the points, we got this one's strong, this one's strong, this was kind of weird. This is a little bit humped. This is pretty strong. So it looks like, just looking at this, it looks like our factors in our model are going to be FGA, FTA, and X3P. If you just go like, I'm just going to scan across here, where are there strong relationships between our response variable and predictor variables? Okay. Now, another way to take a look at it is to use this parallelogram. Now, I talked about this already in a different session. I can't remember if it was required or not, but I'm just going to say, quick introduction. We're going to load a package. And in R, there are many different packages. There's, I don't know how many. Somebody look it up. 500, hundreds, let's just say hundreds of packages, because people are so busy working on stuff in R, and it's open source. You can do whatever you want. You get really excited about something like, oh, I work with this sort of suite of variables all the time, and what I really need to be able to see is this kind of thing, and so I'm going to write up this code, and rather than just write that code every time, I'm going to have shortcuts in the code, and then I'm going to, well, why not just share that with people so other people can take the same shortcuts I'm taking? That's basically what packages are. There's lots of them, and so the way you would do it is like this: install packages. That's the simplest thing, and it's going to ask you for a crayon mirror. Just pick one closer to you. You could also actually, if you know exactly the package you want, you can write it like this: install.packages, quotes, and then the name of the package, and then it will install. And then I can't do it now because I already have it installed. And then you're going to say library when you want to activate it, when you want to turn it on. So at the end of your session, it'll still be installed. You want to install it each time, but you do have to like tomorrow or next week, if you wanted to do this and you'd install the package, you just want to write library core plot to turn that package on. Does that all make sense? Hopefully that makes sense. Okay, so so we can use this LBJ NUM that we subsetted already right here, and we can run it through. We can create this. This is basically the same thing as we've already done. We've done this correlation matrix, but just make the code work. Oh, and by the way, this package was discovered, or this diagram was discovered by a former student in the class named Janae Adams. What happens is, if we're lucky, if I'm lucky, and I've done my job, then people in the class start getting antsy and start saying, well, I'm going to make up my own stuff and start exploring stuff. And later you have techniques and stuff that I don't have because you've been on Stack Overflow, or you just went to Google and typed in like, and learned things that I don't know. And so I learn stuff from students all the time. So here's an example. This is a Janae Adams parallelogram. She figured this out, not me. And so this is the code. This is exactly how she coded it. So you do it like this. This is just defining RES as this correlation. It's basically saying, give me a matrix of Pearson correlations of all the variables in this num LBJ, and then we can do this core plot, which works like this. I did this in a separate lecture. So now, stronger positive correlations are dark blue, negative correlations are maroon. And we can just view across points. Go, aha, here, not sure about that one. These are the three really strongest ones, FGA and X3P. This gives you a notion of what factors are going to be in your final model. Again, what's going to happen at the end of this is, and what your task is multiple regression is, you've got a pool of variables. You have to decide which ones stay in the pool and which ones come with you, which ones are in your model. This is pre-work, exploratory work before, to make sure that you have some notion of what's happening in the data set. I would not encourage you to build a model before you've taken a look, take a peek, always take a peek. And this is a nice graphical method by which you can do that. Now, we don't have any answers here, but we do have an idea. So you're not just flying blind, because we're going to kind of be flying blind next. Okay. So based on these efforts to scan, you can start to build a concept of the important variables in your data set. So there's an extent to which now, if we go back to this business, that's all of this part here. Examine the overall correlation structure, so that you have an idea. And what I might do, if this was just, we can't do it now, but if I had a big data set I was working with, what I would do after taking a peek at this, and I didn't know, so you know what these variables are, but this is something like, oh, this is pH in beetle density or something, or seedling density, or some microbial thing. You don't even firmicutes or something that you don't know, you don't understand. The next thing I would probably do is try to look at individual relationships. I might draw up some linear regressions and chase it that way a little bit too, as an exploratory process before I start to say, okay, now let's build a big model. Now, the next thing I want to do is introduce you to another package. And again, the purpose of this package is helping you simplify from a pool of potential variables to a smaller subset of variables that you can use to build your ultimate multiple regression model that you're going to present to the world. Oh, I've explained the gut microbiota of tortoises, and it's this, and this. But you've got 20 variables to start with. And this is a shortcut, and you're not going to get this anywhere. This is like McEwan special, okay? I don't know anyone who would do this, but I think this is extremely useful, actually. So we're going to install another package, and the package is called Tree. You can do it the same way we did before. You select the CRAN window. Maybe you've already have the CRAN window selected. You don't have to do it again. You do go install packages Tree. I've already got it installed, and then I'm going to say library tree. Okay. So what we're going to do is generate a tree. Actually, it's going to look like a cluster diagram. That's going to present to you the variables that might have the strongest relationship with your response variable. This is a technique called classification and regression tree analysis, CART. C-A-R-T, CART. Now, you can use CART. CART can be like, I'm going to use CART for all my stuff. I mean, it's very powerful. We're not going to use it really here, except for this one thing that it can do that's super nifty, which is if you just throw all of your data into a regression tree and say go, it will give you a visual, spit out a visual representation of a tree of relationships, and you can go, where are the important variables that I might want to include in my future regression or multiple regression model. So once you've got it installed, this is what you do. You just run this model, and then we're just going to plot it. Plot model, text model. So we set up the model like this, and this is what I mean about shortcuts. So once you've got tree installed, tree knows what this is. If you don't have tree installed, R is going to be like, huh, bro, I don't know. But if you've got it installed and you run this thing, you end up with this. This is what's going to be generated. So type the code, run the code, generate. This is a regression tree. Got it? Okay, this is an awesome thing to look at. Here's what this thing does, and this is I strongly recommend this. If you've got multiple variables, you can just run it. You can dive into it if you like. I really want to do regression tree analysis, regression classification. Good, chase that. But if you just like, I got all these variables and I kind of don't know what to do. Parallelogram, I taught you from Janae Adams, and this regression tree is really great because here's what's doing. It says what's the most important variable. That's where you're going to get these breaks. This is dichotomous, so it's going to break one way or the other each time. And so here's the dividing line. You go this way or this way. And so what this tells me is FGA is almost surely going to be in my final model. Then we're going to have X3P, and then maybe FTA, and then down here are some other things. We've got DRB over here. Now, here's what's really amazing about this is giving you breakpoints, not just like here important variables, but what's going on in those variables. So this says FGA greater than 18.5. So more than 18.5 field goal attempts, we go this way down the tree. Then we go greater than 2.5 3-point attempts, we go 33. That's points. That's the response variable. Is this awesome or what? So you go, wow. And then all the way down here, 14.8. So you have less than 18 field goal attempts, less than 2.5 3-point attempts, less than, this is FGA is appearing in here twice. So I would stop there. But anyway, 3-point attempts or free throw attempts are here down to 14.8. Again, if you want to chase down a regression tree as a, in a formal way for your data set, you can't do it like this. You gotta read about that package and get a book, flip through it. But for our purposes, this is super helpful for understanding what's happening in the data set and what you should be thinking about. So if you do the Janae Adams parallelogram and you do this, you should probably know before you ever start the multiple regression kind of what's happening in your data set. This is just exploratory data analysis prior to model building. And again, you wouldn't do this like in an afternoon. This would be something you work on for weeks probably, because you've got this precious thesis data you've been working on that you care about. You need to chase this stuff down. So we have good information based on all of this. As FGA, FTA, and X3P are all important variables. So we go, okay. Interesting. So now we've got all of this information. Let's go back and actually build a multiple regression model. So now that we've done this exploration, we're going to pursue this big model and follow the sort of the next steps in the process. So model building and testing. So first, we're going to write a full model that contains all of the variables. Now, again, someone might have a package they want you to use or some other way of doing this. Good, no problem. But here's one way to do it. So write this full model. This has all the variables in it. This is all the variables in the LBJ NUM data set. And just run that. Over here, it will say, in the console, it will say, okay, I got it. Okay. Note here, I have deviated from the typical notation in class by putting the data definition at the end of the equation. That's this. Instead of putting a dollar sign, so instead of FGA LBJ, I put data equals LBJ. I think this is useful here because we want to be able to see the variables in the equation we are writing. Okay, so here's a way to perform a stepwise assessment of the variables. Note that the default is forward selection. Remember I mentioned forward and backward selection. So we're going to use, so we've defined this model, full equals. And now we're going to go, okay, let's run a stepwise the stepwise process, both regression, focused on this model, which we've defined here, step full. And this is what you end up having over here in the console. Here's the full model. Points equals all of these things. Here's kicking out one of them, blocks, kicking out another one, kicking out another one, kicking out another one. This is this process, the stepwise process. Okay, this is actually not forward selection. This is backward selection. Doesn't really matter. Either way. And here is AIC. This is a CACI information criteria. We want the smallest one. So this is going down as we go along here. That's good. Okay, I got a call there. I don't know if I can stop the recording. I tried. We'll see. Also, I wanted to share with you, because we're just now looking at AIC. You can look up this yourself and go into the details, but here's the person who invented it, this person. Good job, man. You did it. Yeah, so so we want to look at for the smallest AIC in our model. And so if we follow this stepwise procedure, we write the model, then we hit say step, and then we hit summary step like this, or we hit step, and the step will shows us each step over here, and it shows reducing this much, AIC of these different variables. And we want the smallest AIC in the model. The smallest AIC is this one, 203.19. And we can hit summary, and the summary will show us here is these different factors in the model and their relative significance, and also the overall adjusted R-squared 0.62. So what this stepwise procedure showed us is that FGA, FTA, DRB, and X3P are what belong in our final model out of those potential explanatory variables. Now, that's what we thought, except DRB. That's kind of weird. What's that doing? So we're going to have to chase this down even more. So this is like the next step I would suggest. The next step I would suggest is writing a fit for each of these one at a time. So this would be like we did a backward selection before. This is kind of like forward selection. So fit one is just points FTA, data LBJ, summary fit one. Okay, significant. Fit two, we added X3P to it. Summary fit two. Fit three. Summary fit three. Fit four, this is with all four variables. We can write the summary for fit four. So type that code in and run those summaries. And again, you see them over here. Done, worked. Now we can use ANOVA to assess all these models at once. ANOVA fit 1, 2, 3, and 4. So we're going to actually assess the models, model 1, model 2, model 3, model 4, and check out the p-values. The fourth model is significant. but is considerably less significant than the others. Now, let's also take a look because we have to figure out what to do with DRB. So here's the summary fit 3 that does not include DRB. That's here. That's just FTA, X3P, FGA. The R squared is 0.61. If we include DRB, the R squared is, I should look at the adjusted one. It's 0.62 because we're looking at adjusted R squared in this case. 0.59 versus 0.62. This is a very small increase in the R squared. So we do not gain very much power at all from including DRB in this model. The next thing I would do is take a look and see if this makes any sense. So let's take a look at DRB and PTS points. This looks like nothing. We can do a core test. We can do an abline. We can write a model of just those two and summarize that. No. So if we just, and here's the type the code, write the code, run the code. So now is the point in the process where you would probably want to apply Occam's razor. I'm not including DRB in my final model. I'm saying the final model is this one. Adding DRB, while it is significant, doesn't make any sense. Why it's there, I can't tell you. It does increase the fit a little bit, but in this case, and this is the task of you as data analyst, is to figure out which models to include. And in this case, I would not include DRB. I also wouldn't look somebody in the face and say, you're going to get more points by getting more defensive rebounds. It's just like, just doesn't make any sense, right? Now, this is easy, relatively easy, because these are basketball values, which we all understand. And so it's kind of easy for me to say that. It's going to be harder for you to apply Occam's razor to your data set if it's some variables you don't understand. But hopefully the process I've led you through will make that possible, or at least provide some guidance. So that's all I have for now. I might later give you this, I might circle back to a multiple regression with urban forest, but I do just want to show you an example of a data set that you might encounter as a researcher. This one has all of those rows and enough columns that it has to cross the page 3 or 4 times. This is a situation where you would find yourself in, possibly, where it would be incredibly helpful to have some way to narrow before you get started building that full model. I mean, this is just too many. It's really too many. There's too many variables to analyze in a regression model or multiple regression model. You would have equals in 20 or 30 things there. And one thing you can do is use this parallelogram. So if you end up with a data set where you've got many variables, and I'm not going to walk through the whole multiple regression process with this, but I just wanted to show it to you as an example of one thing. It's not basketball data, okay? And you don't know what these things are. And we have this tree canopy is the response variable. We have all of these predictors. There's too many to work with. You're going to have to start selecting and narrowing things before you begin building your models. And so this parallelogram, the Janae Adams parallelogram, could help. You go, okay, tree canopy, let's go across and see what are the really important ones and what are just not appearing at all. And these are all sort of census data information, like how many people are vacant, how many houses are there per square kilometer. This is a negative relationship with tree canopy. That makes some sense. Anyway, this would be a potential potential avenue for you to go down if you end up in a situation where you have 26 or something variables and you don't know what to do next. But you need to build a model in the end that's simpler. You need to apply Occam's razor and start thinning your data set even before you go through that step process. This parallelogram could be extremely useful. So that's all I've got at this time. And I'll see you in the future.